Today we will study the diode in its simplified models. A diode is the simplest semiconductor device. In fact, it contains a p-n junction, so a diode can be considered as a physical embodiment of a p-n junction. Therefore, a diode must exhibit all the characteristics of a p-n junction. Additionally, as a practical electronic device, a diode has properties related to its manufacturing process and various applications, such as high, medium, or low power ratings, high, medium, or low operating frequencies, and different packaging forms. This is the structural diagram of a diode. The central region represents the p-n junction. This is the circuit symbol of the diode. The two terminals are called the anode and cathode, commonly denoted as A and K. From the structural diagram, we can see that the anode is the terminal drawn from the p-type region, and the cathode is drawn from the n-type region. When the anode is at a higher potential than the cathode, the p-n junction is forward biased, also known as forward biasing the diode. Conversely, the diode is reverse biased. When using a diode, it is essential to correctly identify the anode and cathode. Here are some common diode packaging forms. The terminal corresponding to the special color ring or band is the cathode. This is the packaging of a power diode, showing the positions of the anode and cathode. Because a diode contains a p-n junction, its most typical characteristic is unilateral conductivity. Similarly, the current-voltage relationship of a diode can also be described by the exponential equation we discussed earlier. This is the current-voltage characteristic curve of a typical silicon diode. Segment 1 of the curve represents the forward characteristic, which shows the relationship between current and voltage when the diode is forward biased. It should be noted that when the forward voltage is low, the external electric field has little effect on the internal electric field of the p-n junction, so the forward current remains very small. Only when the forward voltage exceeds a certain value does the current increase significantly. This voltage is commonly referred to as the cut-in voltage or threshold voltage. For a silicon diode, the threshold voltage is approximately 0.5 volts. Once the silicon diode conducts in the forward direction, the voltage change is small even when the current varies over a large range. Therefore, it is often approximated that the forward voltage drop of a silicon diode is 0.7 volts. Segment 2 of the curve represents the reverse characteristic, which shows the relationship between current and voltage when the diode is reverse biased. At this time, the diode is in the cutoff state. When the reverse voltage increases to a certain extent, the reverse current suddenly rises sharply, indicating that the diode has entered reverse breakdown. This corresponds to segment 3 of the curve, where VBR represents the reverse breakdown voltage. Note that the exponential equation does not account for reverse breakdown. Every practical diode has specific operating conditions and characteristic parameters. Manufacturers provide model numbers and related data for various diodes in their product datasheets. These datasheets typically include parameters such as maximum ratings, electrical characteristics, thermal characteristics, various characteristic curves, and packaging information. This shows a sample portion of a diode datasheet. The parameters provided in the datasheet form the basis for correct usage of the diode. Here we will briefly introduce a few key parameters. The maximum rectified current refers to the maximum average forward current the diode can handle during continuous operation. The reverse breakdown voltage refers to the voltage at which the diode undergoes reverse breakdown. The datasheet usually only provides the maximum reverse operating voltage, which is typically about half the breakdown voltage. The reverse current refers to the current when the diode operates in reverse cutoff mode. The smaller this value, the better the diode's unidirectional conductivity. The interelectrode capacitance mainly reflects the capacitance effect of the diode's p-n junction and is proportional to the junction area. Since power diodes need to carry larger currents, their p-n junction areas are relatively large, and so is the interelectrode capacitance. However, high-frequency diodes have relatively small interelectrode capacitance and can only carry small currents. When the external voltage applied to a diode changes from forward to reverse, the excess carriers accumulated on both sides of the p-n junction need to dissipate, resulting in a large reverse current. Only after a certain period will the reverse current decrease to the cutoff level. This time period is called the reverse recovery time, usually denoted as TRR. In the figure, IF is the forward current, and IRM is the peak reverse recovery current. When designing circuits with diodes, how should we analyze and design such circuits? The current-voltage relationship of a diode follows an exponential equation. If we were to use this relationship directly for analysis, it would involve solving nonlinear equations, which is highly complex and impractical in engineering. A more practical engineering approach is to use simplified models of diodes to replace the exponential model when analyzing and designing circuits. The idea behind constructing simplified diode models is to use piecewise linearization to approximate the nonlinear relationship of the diode with segments of linear relationships, thus converting the diode circuit into a linear circuit for easier analysis. Next, we will introduce several simplified diode models. The first is the ideal model. In the coordinate system of the diode's characteristic curve, a vertical line overlapping with the positive y-axis represents the forward voltage-current relationship, while a horizontal line overlapping with the negative x-axis represents the reverse voltage-current relationship. This constitutes the ideal diode model. In other words, the ideal model uses two lines coinciding with the coordinate axis to replace the exponential curve, achieving linearization. The ideal model implies that the diode has zero voltage drop when forward conducting and zero current when reverse biased. The dashed line in the figure represents the actual exponential curve of the diode. It is clear that replacing the actual model with the ideal model introduces a certain degree of error. The ideal diode model is quite unique and is commonly represented by a solid triangle symbol. In circuits, an ideal diode behaves like an ideal switch. When forward biased, it is equivalent to a closed switch with zero voltage drop, and the current depends on the external circuit. When reverse biased, it acts as an open switch with zero current, and the voltage across it is determined by the external circuit. Despite the error introduced, this model is still feasible in circuits where voltage levels are relatively high due to its simplicity. The second model is the constant voltage drop model. Shifting the ideal model's vertical line to the right to match the exponential curve gives the constant voltage drop model. This model means the diode only conducts when the forward voltage exceeds a certain threshold. Otherwise, it remains in cutoff. Once conducting, the voltage drop remains constant. For silicon diodes, the forward voltage drop VD is typically about 0.7 volts. This model can be represented by an ideal diode in series with a voltage source. The constant voltage drop model considers the diode's forward voltage drop. Compared to the ideal model, it is much more accurate while still being relatively simple, making it widely used in engineering practice. The third model is the piecewise linear model, which modifies the constant voltage drop model by tilting the vertical line to better match the exponential curve. The slope of this segment represents conductance, and its reciprocal is resistance. Clearly, the piecewise linear model offers higher accuracy but is more complex. Its circuit model consists of an ideal diode, a voltage source, and a resistor in series. The above three models are all large signal models, which means they are equivalent models for diodes operating under large voltages and currents, and they only reflect unidirectional conductivity without considering reverse breakdown. When analyzing diode circuits with these models, the key is to determine whether the diode is conducting or in cutoff. The fourth model is the small signal model. When the voltage and current of a diode only vary within a small range, a model can still be established. This is called the small signal model. For example, if the diode operates such that its voltage and current vary slightly around a Q point between Q' and Q double prime, then a tangent line passing through the Q point can replace the exponential segment between Q' and Q double prime. This tangent represents the diode's linear small signal model. This tangent line can be equivalent to a resistor, whose value is the ratio of voltage change to current change. According to the diode's exponential equation, differentiating current with respect to voltage gives the conductance. Furthermore, since the Vd at the Q point for a silicon diode is about 0.7 volts, much larger than the thermal voltage Vt, the constant 1 in the exponential expression can be ignored. Substituting back into the conductance formula gives the conductance at the Q point, which is the slope of the tangent line on the characteristic curve at that point. Note that in the conductance formula, the capital letter ID refers to the current at the Q point. The reciprocal of this conductance is the small signal resistance Rd. Regarding the small signal model, keep the following points in mind. First, the resistance in the model is the ratio of voltage change to current change, so it is also called dynamic resistance, incremental resistance, or AC resistance. Second, the model is built based on the Q point, and the dynamic resistance depends on the current at the Q point, which lies in the forward conduction region. Third, the voltage and current at the Q point are DC quantities. This circuit state is called quiescent, and the Q point is also known as the quiescent operating point. Appropriate simplification allows for more convenient circuit calculations. In life, we should also practice stress reduction. As long as it does not affect normal living, working, or studying, don't put too much pressure on yourself. The goal of decompression is to move forward better. That's all for today's lesson. Thank you all for listening.